Now, so far we've looked at double integrals, and we've looked specifically at integrating over a region. And when we started, the regions were nice. We called them capital R, I think, for a rectangle. At least that's probably what the book did. X, Y, that satisfied the property that X is stuck between some constants A and B, and Y, and Y was stuck between some constants C and D. That's what we started with. But then we also started looking at other regions that the book has called D instead. And what happened was these were sets of all points of the form x comma y, where a was still stuck. Sorry, x was still stuck between two constants a and b, but then like y was stuck between the values of two functions of x. So like g sub 1 of x, g sub 2 of x. We also saw integrating over regions where now y was stuck between two constants, say c and d, and it was x that was stuck between two functions of y, such as h sub 1 of y at the small side and h sub 2 of y on the big side. Now what we're going to do, though, is we're going to try something new. We're going to integrate over a region. Capital R, we'll still use R, but here's the funky thing. This will no longer be ordered pairs x, y. This is going to be r theta. You kind of can catch the drift of what's going on. We're going to use polar coordinates now to describe the region we're integrating over, where theta, sort of simple case like back here, is stuck between two constants, which we'll call alpha and beta. And the value of r is stuck between two constants, which we'll just call a and b. Or we're going to start integrating also, just to kind of preview something that looks more like this, a slightly more complicated thing, integrating over all points written in polar coordinates of the form r theta, where theta is again stuck between two constants alpha and beta. However, the difference now is r might be stuck not just between two constants, but between two functions of theta. So h sub 1 of theta and h sub 2 of theta. Okay, so let's draw a picture of what this looks like. So I'd like to draw a picture of r, of this first thing here. So just generally speaking, what this looks like is, well, so I know we're in polar graphing, but we still tend to draw x and y axes to try to get a sense of what's going on. And if you'll notice, theta's stuck between alpha and beta. Well, okay, let's draw theta is equal to alpha and theta is equal to beta. So the angle is alpha. That might look like, I'll just draw this dotted, like maybe like this. Okay, so all along here, sorry to draw this dotted for now, but this angle here I'm saying is theta is equal to alpha, but the place I'll label this is over here. Theta is equal to alpha. So all those points on this dotted line have angle alpha. And then let's just somewhere over here, maybe, like draw in all the points that are on a different angle. Again, what's really going on is this angle there is beta, but just so the picture doesn't get too messy, we'll label this theta is equal to beta here. And then you'll have this r is stuck between a and b. Well, remember, r is actually the distance away from the origin in polar coordinates. So maybe if a is here and b is, let's just say, right there, then I'm going to try and draw a circle centered at the origin of radius a. Let's see if I've done a good job or not. That's meant to be a perfect circle. Yeah, that was okay. And then a circle of radius b. I'm trying here, folks. Get a thing that looks like this. Okay, I won't continue drawing that all the way around. The region that I'd like to focus on is this right here. Okay, so that region, let me shade this in. This, folks, is capital R. Okay? Now, within this region, I'd like to just look at one little sliver here. So it's, let me try this again. In the picture, in fact, you know what? I've got a computer. Why don't I do everything I can with it here? So what I'm going to do is draw two line segments that are meant to be completely straight. These line segments, if I continued them, they should go through the origin perfectly. And then this way, I'm going to have a slightly curvy thing. These should be arcs that are part of a circle of and that the circle should have as its center the origin. Picture doesn't look very convincing, perhaps, and I apologize about that. But what I'd like to do is take that little thingy here and then zoom in a lot, so that we can really see a good picture of what's going on here. So I'm going to take that tiny little patch right here and make a very, 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 very big picture of it that looks something like this. Whoops, let's try this again. Like that. Okay, so like this edge is that edge. I've just blown it up so big in the picture. Okay, I'd like to label a couple things in here to try to make sense of some of the things that the book talks about. By the way, let's just for reference, that point that's right in the middle, let's just pick that right there. Okay, and what we're going to do is I'd like to just note that then along here, this is a value of R. I'll call that R old, and then right here is another value of R. All along here. So let me call that R new. And then the at this specific point that we've sampled in the middle, we'll call this R sub I star. And the key point being that the distance between R value and R value should be called capital R. This is like, change in y, is is the new y minus the old y. Same deal here, delta R. And then we can do the same thing this way. So all of the points along here, they had a certain theta value. So let's call that theta sub old. And then all the points along here were a certain theta value. Let's call that theta sub new. And, right in here, also there's a certain value of theta. And I guess we could call this theta sub I star. Doesn't matter all that much. But the key thing is this distance from here to here, and I am trying to draw this a little bit curved, like that. That should be the change in theta. So it's the, theta new value minus theta old value, right? So, okay, let's talk about the area of this. Now, again, this is a tiny little piece. It's a tiny scrap of what we see back in this picture over here. Let me maybe highlight with the mouse right now, that part right there. So how can we compute what the area of this looks like? So the area of this tiny little piece, it's really, if you think about it, this is part of an annulus. Yeah, so this is you think of like the area of a circle minus the area of another circle with a slightly smaller radius. So this should look something, roughly speaking, like this. 1/2 times the new radius, so R new squared, but not the whole circle, right? So we only have a certain sector of it, and that angle here is actually delta theta. So this should be times delta theta, because we don't have the whole circle. It's like a certain piece of pie. And then we should subtract off 1/2 R sub old squared delta theta. Now, here's what we can do to this, is we can factor out a 1/2 and factor out a delta theta, and what's left inside is R new squared minus R old squared. And we can, still copying the 1/2 and the delta and the change in theta, what we can now do is, well, this is a different squares, right? So R new plus R old, and then R new minus R old. Here's the thing. This first part right here, R new plus R old divided by 2, that's the average of the R values, right? So that's actually this R value right here. That's all this first part. Yeah, so let's reorganize this slightly. This first part right here, that's just R sub I star. R sub I is the average of R new and R old. And then what about here, R new minus R old? Well, we labeled this here. This is delta R. So that part is delta R. And then let's copy down delta theta down here. Okay, so here's what we actually have. This great thing going on is now the volume. So from this little piece here, this is the area of one little patch. But now the volume under the graph of z equals, we won't use f here, but we'll just use a g as the name of the function. G r comma theta. So this is a function where the inputs are polar coordinates now. Polar coordinates for the inputs. Or, in case you happen to have another function, f, which is written as xy, but you could replace the x and y, by the way. You could replace the x with r cosine theta and the y with r sine theta. Okay? This volume is, in either case, is given by the following. Now this double limit's going to look a little funny, but it's going to be limit m approaches infinity, limit n approaches infinity, sum I goes from 1 to m, sum j goes from 1 to n of f of, so we're going to pick up these values here, but just sample at specific little patch pieces that look like this, and so that's going to be f of r sub I star cosine of theta sub j star, comma r sub I star sine of theta sub j star. That function, then copying this thingy right here, we're going to have r sub I star times delta r times delta theta. Oh, okay. So that looks like quite a mess. I'm not expecting you to ever compute it like this. This is just my way to point out that this ends with this that came from up here. Okay. Now, where did this all come from? Like, it really was. It goes back to like this difference of squares thing back here that led to the average of the two r values and the subtraction between them. The key point now is that this circled thingy right here, you'll notice, when you take this limit of this Riemann sum, right? This is going to actually, if this limit exists, we're going to now say this is the integral. So don't worry about ever setting it up like this, but I wanted you to see the end of this, because now, as an integral, we're going to have, if the limit exists, integral from alpha to beta of the integral from a to b of f of r cosine theta, comma r sine theta, r dr d theta. So you'll notice the r star delta theta is now r dr d theta. I think you're going to see a lot of this r dr d theta business. So I know it looks a little funky for now, but you'll get used to it. I think the key thing to say at this point here is this r. Please don't forget the r. That is what people end up doing. Don't forget the r here. And the whole point of this work up here was just so that you see where that r comes from. In the end, to integrate, here's getting a little more to the punchline. To integrate f of x comma y over the region r given in polar coordinates as r theta, where, let's say, just to get a couple more standards in here, let's say 0 less than or equal to a, less than or equal to r, less than or equal to b, and theta is stuck between alpha and beta. And let's just, for one more thing, to make some standards so that things don't cause too many problems, this is really for a technicality. The difference between the two angles, beta and alpha, needs to be between 0 and 2 pi. This is just meant to, don't worry about it too much in the beginning, but if you want to come back and ask what this is about, it's to ensure no funny business of repeating the same region over and over is really what it's about. So to integrate, that'll be written first as a double integral. It's the integral over the region R of f of x comma y dA. Sure, we can write that, but that's going to become the integral from alpha to beta of the integral from a to b of f of r cosine theta comma r sine theta times r dr d theta. And the thing that's a little funky about this process is I would like you to match up the dA with this part right there. And the point that I'm trying to make is we should think of dA as equaling r dr d theta. In the past, dA was just dx dy or dy dx. So what's going on? If we were to follow this method to integrate, there's a couple other points that I think that could be made that would be helpful. There's x here, there's r cosine theta here. And so we'll just make this more procedural and say replace each x with r cosine theta. Replace each y with r sine theta. Okay, and then, as has already been commented here, that dA is going to become r times dr times d theta. So this, I know, looks a little strange, and we will see some examples in a moment, but this is analogous to earlier in the chapter dA got replaced, with dx dy, or dA got replaced with dy dx. Same idea. All right.